Okay, folks. Okay, so let's begin. And you can hear me okay, right?
Yes.
Okay, good.
Yes.
Thanks. Okay, so today we're gonna discuss. We're going to continue discussing the consequences of spin addition, and we're going to start talking about time-independent perturbation theory. So that's the plan for today. And so let's just remind ourselves a little bit what we did last time, which was we sort of derived, I'll say derived in quotes, we derived the rules for spin addition. Really, we didn't derive them. We sort of did an example and then used the process of induction to say that it's a general rule. And the rules for spin addition, remember the idea for spin addition is that the whole point is that we have some many-body wave function, and we want to write it as a spatial part times a spin part. And so the question is, how do we write the spin part? How do we represent it? That's the question we're trying to answer. And so one way is to just write, is to create just a simple product state. Where we have the many-body spin state is equal to a product state of all the single particle spin states for all the different particles up to, say, some nth particle. And in this case, what we have is, this is an eigenstate of these operators, S1 squared, S1z, S2 squared, S2z, all the way to the last one. But for us to add the spins, addition of the spins, what that means, that's the same as converting to a new basis. So we want to convert our representation of our many-body spin state to a new basis. And the new basis are the eigenstates of the total spin operator and the total z component spin operator, where the total spin operator is equal to the sum of all the individual spins and the total z component is just the sum of all the z components for all the individual spins. And so if we do that, then we see that then if we look at that basis conversion, then we're able to derive the rules for spin addition, which is that for two spins, if we want to add two spins, S1 plus S2, and I put a plus in a circle sign because to indicate that we're changing basis, then the rule is that we have the allowed values of S total are equal to, first we start with the sum. I'm sorry, the sum of S1 and S2. S1 plus S2, and then we just ratchet our way down all the way to S1 minus S2. And of course, M total is less than S total and greater than or equal to minus S total. And so, but the...
Sorry, a quick question. Sorry
Yeah.
to interrupt. What was the, I was trying to look through the notes from last lecture, but I couldn't find an answer to this. But what was the motivation for trying to find a new basis state?
Oh, that's a good question. And so the motivation is that I would say two motivations. One is that it makes the symmetry of the state easier to see. And the second motivation is that it's very convenient for doing perturbation theory, which will be our next topic. Although, you know, that's not obvious to see at this point, but you will see it as we go along. Is that cool?
Yeah, thank you.
And so the question then is how to write these new states, the new basis states, which are the basis states S total, M total. How do we write them? And so that's not completely trivial, but what we do is we just we just use the old basis. It's just a linear superposition of the old basis states. Linear superposition of old states. And that's a general concept. Whenever you're converting in linear algebra, whenever you're converting from one basis set to another, the new basis set you write as in terms of the old basis set. That you've all done that, although you might not remember, but that's sort of like a common mathematical trick. That's how you change basis. That's what it means to change your basis. And so what we do then, so in general, we can write that the total spin state can be written as a linear superposition of the old product states, and so that means it's a sum over M1 and M2, and there's a coefficient, and then we have the old product states S1, M1, S2, M2 for two, and this is for addition of spin 1, 2 spins. So if we're adding two spins, then the total spin is going to equal this linear superposition over all of the possible product states. That's the old basis. But it's a restricted sum because remember the new eigenstate is an eigenstate of S total Z. It has a well-defined S total Z. So that means that M1 plus M2 has to equal what? Now I'm asking, yeah?
S total.
No, not in general, because M total, remember, M total can be any integer between plus S total, whoops, and minus S total. So M total can be any integer, but now I'm asking about this sum, M1 plus M2 for the product state has to equal what?
MT.
Exactly, that's exactly right. Because the product state is an eigenstate because the product state is an eigenstate of S total Z. And so that means that M1 plus M2 equals M total. So this is a restricted sum. So in the superposition, there's only, we don't have all basis states in the superposition, only a restricted amount. And this coefficient then is a special coefficient. This coefficient is going to depend on all of these values. It's going to depend on M1, M2, M total. It's also going to depend on S1, S2, S total. So that coefficient is a funny looking coefficient. And this coefficient has a name. What do we call it? Does anybody know the name of that coefficient?
Clebsch-Gordan.
Exactly. That is the Clebsch-Gordan coefficient. Clebsch-Gordan coefficient. And so we actually, what we did last time when we did it for the, for the singlet and triplet states, we actually derived the Clebsch-Gordan coefficient for the most simple case, but now I'm writing it in general. And so what we did last time was the simplest case, and I'm not going to rederive the whole thing, but I just want to write down some of the results. The simplest case that we did last time is if, and I would say also the most important case too. This is the simplest case, but also the most common, the most important case, is that S1 equals 1/2 plus S2 equals 1/2. And so then when we did our rules, we see that we did it through the long, hard way, but we saw that the total, S total is equal to the sum, which is 1, and then we ratchet down all the way down to the difference, which is 0. So we got these two possible spin total states, and then when we derived them, we saw that for S total is equal to 1, we saw that we got 3 states, which was up, up. And remember, this is for particle number 1, and this is particle number 2. This notation, don't forget what this notation means. And this state had M total equals 1, and then we had 1 over square root of 2. And then we had up, down, plus down, up. And that was M total equals 0. And then we had down, down, which was M total equals -1. All right, and so this is 3 states. So we call it the triplet states, because there's 3 triplet states for 2 spin 1/2 particles. And that's a very famous name. You guys, if you stay in physics or you do anything like in chemistry or physics that involves quantum mechanics, then you often will hear people talk about triplet states. It's a very common lingo. And then here, we then have the S total equals 0 state, which we derived is up, down, minus down, up, which is M total equals 0. And that's the singlet. We call that the singlet state because there's only one S total equals 0 state. All right, now something to notice. Let's take a look and let's notice the symmetry.
Professor?
Yeah.
Would you mind scrolling back up to the Clebsch-Gordan coefficient just for a second?
Of course.
I just wanted to clarify. Originally, you had written that we're summing M1 comma M2. So, and then you made a point about we're actually constraining the summation. I just want to reiterate to make sure I understood. So the summation is not all of M1 and all of M2. It's the summation of their sum.
It's a summation of all M1 and all M2 that satisfy this constraint, that M1 plus M2 equals M total. Does that clarify?
Yes. Okay. Thank you.
Okay.
Another question for there is the Clebsch-Gordon coefficient supposed to just be the normalization constant?
It is the normalization constant, but it's much more because these states are eigenstates. And so in order to make sure that this constrained sum is an actual eigenstate, we have to have just the right amount of each one so that they satisfy the condition of being an eigenstate. Does that make sense?
Yeah.
Okay. And these Clebsch-Gordon coefficients, how do you get them? Mostly what you do is you look them up in a book. Look up in book. You know, people typically don't derive them. You just kind of look them up. Okay, so now let's go back, and this is the simplest example, the singlet and triplet states for 2 spin 1/2 particles, and let's notice the symmetry of these states. So consider the S total equals 1 states, the triplet states. Then let's look at this state, up, up, and let's hit it with the exchange operator 1, 2. What does that give us? What is the new state when we do this exchange, when we exchange the labels? What is the new state? Yeah, it's exactly the same thing. And so then that means that the symmetry is what? The symmetry is what? Positive or negative?
Positive.
That's right. So it's so we call it symmetric states. And you can see the same thing, like do the same thing for this one, P12. Let's do it for the other one, the up, down, plus down, up. And when we do it, when we do the math, we see that the first term converts to down, up. That's what it means to exchange the labels. It becomes down, up, and the second term becomes up, down. But look at this new state and look at this old state. And what can I say about those two states?
It's the same.
Yeah. And so once again, you see that the symmetry is positive. So, and of course, you could do the same thing for the down, down, right? P12 down, down is equal to down, down. So the point is that the S total, the triplet states are symmetric. And now let's take a look at the singlet state. And let's hit that with the exchange operator. And so that state is up, down, minus down, up. And so when I hit the first one, then up, down turns into what? Someone tell me.
Down, up.
Yeah, perfect. And I have minus sign, and the second one turns into up, down, because I'm exchanging the labels. And you notice that this is, now what's the relationship between this and this? What's the relationship?
Is it anti-symmetric?
Exactly. It's equal to negative 1 over square root of 2 up, down, minus down, up, the original thing. And so that means that the symmetry is negative. And so this state is anti-symmetric. And that has big consequences. That has big consequences because let's consider this for a moment. Because now let's consider what are the physical consequences of this? Let's think. So suppose we put 2 electrons into a box. And here's the box. And you know, I love to draw these boxes. It's just the simplest way to think about quantum mechanics, in my opinion. So I have state A, B, C, and and those are the energies, right? You know, the energy goes up as we go up. And then I want to put 2 electrons into a box, but these 2 electrons are, you know, that's electron number 1, and this is electron number 2, and they have spin, S1, S2. They're both spin 1/2 objects. And so I'm going to ask you now, what is the ground state? And I'll give you a hint. The ground state, I'll call it like this, ground state is equal to, I have a spatial part times a spin part. And that's my hint to you. And so I want, the ground state means the lowest energy state. So you remember the rules of constructing many body eigenstates. Basically, we just throw the particles into states, into whatever states, and then we will basically construct the Slater determinant from those states. Remember, that's the rule. So I have these 2 electrons. So which states do I stick them into for the ground states? Somebody tell me.
For the spatial, is it anti-symmetric? And then for the spin, it's symmetric. So it'd be the anti-symmetric tensor product with the triplet state.
Okay, but I'm asking you, I want to step back a little bit. So you're sort of jumping like to the final answer, but I just want to step back. I just want to ask the first question. I got 2 particles. What states do I throw them into for the box? Which states?
Both of them can be in state A, but with opposite spins, or like with different, with m equal to plus or minus 1.
All right, yeah, because that's the point. Because one place I could put them both here. But in the old days, we would say, no, you can't do that because now they're both in the same state. The Pauli exclusion principle says that that's not possible. So then in the old days, you might say that they have to go like this, right? But the point is that now we can put them in this state because the spin allows us to satisfy the anti-symmetry rule. The spin now allows us to satisfy the anti-symmetry because now if I put them both in the same state, I know then that the spatial part is, can someone tell me what the spatial part is? If both particles are in the same state, what's the many-body spatial? What's the spatial part of the many-body wave function? Basically, do the Slater determinant in your head and tell me the answer. Tell me the answer. Come on, can't you do a Slater determinant in your head?
Is it psi A, psi A?
Exactly. That's right. It's psi A of x1 for particle 1 times psi A of x2. That is the Slater determinant. I mean, if you constructed the Slater determinant and worked it all out, that's what you would get. And this is, and so what's the symmetry of this? Somebody tell me.
Symmetric.
Exactly, it's symmetric. And normally we would say that's not allowed because the total symmetry has to be anti-symmetric. But now we can allow it because what we do is we do a trick and we say, we ask ourselves, what's the spin part? So now somebody tell me what's going to be the spin part of the wave function for this state? Using the tricks we just learned. I got 2 spin 1/2 particles. And there are many possible spin states, but which one should we take? Somebody tell me.
The singlet?
Yeah, exactly. Exactly, the singlet. 1 over square root of 2, up, down, minus, down, up. And the reason we do that is because the symmetry of the singlet state is what? Tell me.
Negative.
Exactly, it's anti-symmetric. And so that means that the symmetry, if I exchange P12 of this state, I'll call it psi A, psi A. I'm just trying to do shorthand. It's just so tedious to write. Up, down, minus, down, up. So what is this? What happens when I hit this state, this product state? It's not a product state, but it's this wave function, this many body wave function. What happens when I hit this many body wave function with the P12 operator? What do I get?
-1 as an eigenvalue.
That's exactly right. I get -1 times the same thing. And that's because the symmetry of this part is plus, and the symmetry of this part is minus, and plus times minus is minus. So it's anti-symmetric. So is it allowed so does nature allow it? Yes or no?
Yeah.
Yes.
Yeah, nature allows it. And so the way we justify that in our mind, the shorthand that you always see, like, this is the correct thing. We just did it. We just anti-symmetrized the many-body wave function. But what people often say is they'll go back to this little simple box picture and they'll say, well, this guy went spin up and this guy spin down. That's what people say, because now I have two different particles. They're not the same state, because I have particle 1 has spin up and particle 2 has spin down for the anti-symmetric, which satisfies the Pauli exclusion principle. That's sort of the shorthand. But I just want you to appreciate that this is not fully correct. The shorthand is not fully correct, because the correct answer is that the spin part of the many-body wave function is in a singlet state, which is really this funny thing. The singlet state is this. And this is actually very special, because I do just want to make the comment that this very special state, this many-body spin state, this singlet state, is actually quite special. It's so simple. I mean, we derived it, we wrote it down, but I just want to point out that it's entangled. So this is an entangled state. And entangled, the textbook definition of entangled just means it's not a product state. That is the formal definition of the word entanglement, which I'm sure you've all heard in one context or another without realizing it's such a trivial thing. So the actual concept of entanglement is trivial. It just means that the state is not a product state, because this is a product state. Up, down is a product state, and down, up is a product state. But up, down plus down, up is not a product state. And because a product state is a state just that is equal to just a product of a bunch of states, phi 1, phi 2, etc. It's the product of a bunch of states. And so and if that doesn't make sense, you go home and play with it around a little bit, just to convince yourself that this sum is not a simple product. It's a sum, and a sum is not a product. I mean, it's like so trivial, but it is what it is. It's profound and trivial at the same time. And so this is an entangled state. Now, when people talk about quantum information theory and quantum computers, entangled states are very important because they have lots of important consequences. But for this class, I am not going to discuss the consequences of the entanglement. To understand that, go take a course on quantum information theory. But what I want to do for this course is just point out, hey, this is an entangled state. Entangled states are very common all over the place. And the reason they're very common is because this situation, when I put 2 electrons into a box, is a very common thing. 2 electrons are often in a box. Can people tell me what that box might be? Box equals what? Like
1s orbital.
Say it again.
1s orbital.
Yeah, exactly. 1s orbital, in which case the box has a name. If it's in the 1s orbital, what do you call that box?
Is it helium?
That's exactly right. So that's helium. So this is exactly the situation for helium, and we'll talk about that a little bit in a minute. What's another box?
A covalent bond?
Yes, exactly. Covalent bond. These are the two most common boxes. I would say the covalent bond is the most common because every chemical bond has covalent bonds. And within a covalent bond, then where the covalent bond is basically just, you know, two nuclei of two atoms where you have this bonding orbital. And I'm not going to derive the bonding orbital, at least not today. Maybe we'll do it another day. But that's the bonding orbital, and the two electrons are sitting in that bonding orbital in a singlet state. So the electrons in every bonding orbital are in a singlet state. And so, you know, you're made out of bonds, covalent bonds, and that means that you're highly entangled. You are highly entangled because every bond in your body is an entangled state. Okay, so let's consider an example. So,
sorry, Professor,
yeah.
Before you go on, could you clarify why exactly we had to choose the singlet instead of the one of the triplet states that also had these like it was a center triplet state? Like why choose the?
The reason is because I asked for the ground state, the lowest energy state, and by putting the two guys into A, it was the lowest energy. For example, if I would have put them into this, A, B, C, like this, that's an excited state. Do you see what I'm saying? So the lowest energy state had them both in the A, in the A state.
Right. I meant for the spin state. Why not use, because the way I see it, we need sort of a superposition of the up and down and the down and up. But why couldn't we just put a plus sign instead? And
because that would give it the wrong symmetry. Because
okay, so we need an antisymmetric. We know that already. Okay.
Yes, okay. Absolutely. That's the rule, right? So we have to for a physical state, we need to follow that rule. That's correct. Okay. So now let's look. So I was just talking about the covalent bond for a few minutes, but now let's spend a few minutes talking about helium as an example of this physics. This is an example. So what is helium? Let's remind ourselves what helium is. And so helium is this. I have a nucleus, and the nucleus has Z equals what? Somebody tell me for helium.
2.
Yeah, 2. I gave it away with the picture. And then I have 2 electrons somehow orbiting that at the same time. So that's like the classical picture. But from the quantum picture, what we do is this is the same as a box, because you know I love particle in a box. And so here the box is this. Oops, I didn't draw it very well. This is the Coulomb potential. V of R, well, let's say, what is it? V of R1, R2 is equal to negative E squared over 4 pi epsilon naught times 1 over R1 minus R2, right? That's the Coulomb potential. Where one of these is the proton. So, I mean, this is the Coulomb potential. Maybe I won't write the formula because it's just starting to, because there's actually, it's just starting to get confusing by having all these formulas. But I just want you to see that both of the 2 electrons are sitting in the Coulomb potential. This is the Coulomb potential of the proton, Coulomb potential of proton. And so that's the box in this case. And so what we do is we ask ourselves, what's the ground state of the helium atom, ground state? And so what we do then is we have 2 electrons, S1 equals 1/2. S2 equals 1/2. And we have a box. And so here's my box. It's this Coulomb potential, and it has, and I have the single particle levels. And you know them all. This is the n equals 1 level, n equals 2 level, n equals 3 level. And these are all the particle in a box states. But here the box is an atom. And so the states are as follows. The single particle states are psi, n, l, m, and you guys all did this last semester, so this is review, but you know, you might not have it all memorized. But you have, remember that the atomic states, there's a radial part, NL, and then there's an angular part. Can somebody tell me what the angular part is of the wave function for an atomic state?
A spherical harmonic?
Exactly, it's a spherical harmonic. Y, and this is how I like to write the spherical harmonic, YLM of theta and phi. Because it's spherically symmetric Hamiltonian, so we write it in spherical coordinates. And the energy is this very simple formula minus z squared over n squared. And you guys all derived this last semester, times 13.6 EV. Okay, so that's what I would call the particle in a box states. It's just like giving it a different name, but I want you to see the physics is the same as all that particle in a box stuff I was talking about before. So these states are these little lines I just drew. Each line here is one of these states, and this is of course an energy is the vertical axis here, and this distance is the radial coordinate. So the question that I ask now is, in order to write the ground state for the helium atom, we take those 2 electrons, and which state do I got to stick them into? I got to distribute them into this box. Where do I put them? Somebody tell me. Where do I put them in this box?
N equals 1 state?
How many do I put there?
You could put 2 with different spins, right?
Perfect, that's exactly right. So using this sort of oversimplified notation, I'll just say I put 1 in there, spin up, and 1 in there, spin down. Now I can stick them both in there and satisfy the Pauli exclusion principle. That's exactly right. And so the state, and so you guys remember that for n equals 1, then L equals what? Somebody tell me. The orbital angular momentum of n equals 1 state. And this is, you gotta remember this from last semester. I know it's tough to remember things. Yeah?
Is it 0?
That's right, has to be. And so that means that m sub L equals what?
0.
Very good, very good. Yeah, unfortunately for this class, you're gonna have to remember all these atomic wave functions, all these little rules. It's not that hard, just go review it. And so then this state is gonna be psi 1, 0, 0, right? NLM 1, 0, 0. And so that means that the spatial part, well, actually, let's just do it all the same so it'll be less writing for me. So I'll just say that the psi, the ground state of the helium is equal to, let's write the spatial part. And so the spatial part will be psi 1, 0, 0 of particle 1, electron 1, times psi 1, 0, 0 of electron 2 times what? Now I have to write the spin state. What is their spin state? What is the spin state of helium in the ground state?
The singlet, right?
Has to be, because this guy is symmetric under particle exchange. And so I need to find, in order to make the whole thing antisymmetric, I need the spin part to be antisymmetric. And so hence, I know it's got to be the singlet, because that's the antisymmetric one. And the energy is equal to, let's call this energy E1 for the ground state of one electron in there. So it'll be E1 plus E1, because the two electrons go into that first state. So the energy is just the sum, E1 plus E1 is equal to, you know, twice E1. Okay, that's the ground state. But now what we can do is let's construct the, excited states.
Can I ask a question really quick?
Yeah, of course.
We talked about it last time, but I'm having a hard time remembering. How come we can't use the symmetric triplet states for spin in the anti-symmetric spatial state?
Because when two particles are in the same state, the same spatial state, n equals 1, then you cannot construct an anti-symmetric superposition if both particles are in the same state. There's just no way to do it. So the spatial part, if I put the two particles in the same spatial state, then that spatial state will always be symmetric under particle exchange, because the same function times the same function. So if I exchange the labels, it's always the same. That means that the spin part has to carry the anti-symmetrized part.
So if we put two different particles in different energy levels, then we can have a symmetric spin state?
Yes, and we're about to do that.
Gotcha, okay.
So now let's construct the excited states. And so for the excited states, we do this, and I have my Coulomb potential, and I have my box, and this is the n equals 1, this is the n equals 2, this is the n equals 3. And so now I have my two particles, spin 1/2, spin 1/2 particles. And now for the excited state, I'm going to do this. I'm going to put one of them into the lowest state. Where am I going to put the other one?
N equal to 2.
Exactly. I can put it anywhere above. I could have put it there, or I could have put it there too. You know, I could have done it there, just anywhere above. But you can sort of see, but let's put it there. And so for this excited state, what's the energy? What's the energy of this excited state? Somebody tell me.
E1 plus E2?
That's exactly right. But now let's write it down. What's the wave function for this excited state? Now it's a little bit trickier. Let's write down the wave function. So psi of the excited state is equal to, now let's write the spatial part times the spin part. Okay, so what's the spatial part? Tell me.
It would be a linear superposition of the two product states, psi1.
Which one?
Psi1 and psi2 and psi1, psi2. And then
no. What I meant was which superposition, because there's two possible superpositions.
We would maybe want the symmetric one, since.
Well, actually, let me be more tricky. Let me ask you this. What is the lowest energy excited state where the electrons occupy these two states? The lowest energy. Now, this is sort of a tricky question, which takes knowledge from our last lecture.
The symmetric one.
The what?
Symmetric one.
For the spatial part, I'm asking the lowest energy. What is the spatial wave function for the lowest energy state? And let me ask another question. Should the particles, is it lower energy for the particles to be close, or is it lower energy for the particles to be far?
Far.
Good. So which spatial state makes the electrons further away from each other?
The anti-symmetric one, right?
Yes. So that's the lowest energy one. 1/√2 psi, I'll call it 1, 0, 0, R1, this is so tedious to write, psi 2 LM R 2, and now I got to write minus psi 2 Lm R1 times psi 1, 0, 0 R2. Okay, so that's the antisymmetric state. So that's the antisymmetric spatial state. And then here, because that's antisymmetric, the spin part has to be what?
Symmetric.
Exactly. So what spin should I give it?
Either one of the triplet states?
Exactly. So I'll just write it here like this. Any one of the triplets would be fine. S total equals 1. That's right. So that, and as you can see that you can see that there's a lot of degeneracy here because there's several LMs for the n equals 2. So there's degeneracy, and there's several M totals for the triplet. So that means that this is degenerate. That means that there's several possible states that have the same energy. It's degenerate. But then there's another, but now let's write the next type of excited state, because there's another one which could have been, because we could have chose it differently. We could have chose it so that the spin part is opposite. We could have done it like this. We could have said psi 1, 0, 0, R1, psi 2, LM, R2, plus psi 2, LM, R1, psi 1, 0, 0, R2 times, and then we could have done the singlet, right? We could have done that, in which case this guy is symmetric and this guy is antisymmetric. So will nature allow this state? Is this state allowed by nature?
Yes.
Yeah, exactly, because it's antisymmetric. So you see that there's really two different types of excited states for helium. Helium, there's only one type of ground state. We derived it a moment ago. But for the excited states, there's sort of two classes of excited states. And one class has S total equals 0. And that we'll say is non-magnetic because it has no net spin. But the other has S total equals 1. And that one is magnetic because it has net spin. And they each have names. The S total equals 1 types of excited states have a special name. Does anybody know what it's called? Does anybody remember the name? I mean, you've probably never seen it before, but some of you might have seen it. Has any of you seen it? Okay, I mean, it's not such a common name, but this one, yeah, exactly, very good. How did you know that? So this one is called... I
just remembered paramagnetism.
You remembered it from where?
From chemistry, paramagnetism and stuff.
I see. Okay, well, that's good that you remembered it. So you got the para state, which is the S total equals 0, and the ortho state. I don't even know where these names came from, to be quite honest. I mean, I don't think there's any rhyme or reason to it that I know of. But that's just what some chemists came up with maybe 100 years ago, who knows. Okay, so this one we call the ortho state, and this one the para state. And this is an important thing. So what that means is that if you take helium and you excite it, then sometimes it might be in a magnetic state, but other times it will be in a non-magnetic state. And you really could separate it because you could, I mean, people do this. Like you can take, I mean, I know people who do this like for a living. I mean, you can take helium and pass it and shine light on it to excite it. And then what you can do is take a magnet, and the magnet will cause the magnetic ones to bend if you stick it into a Stern-Gerlach magnet. So you could then deflect the magnetic ones, and then you can have a beam of purely magnetic helium. And then you can use that to scatter, and you can investigate magnetic materials with a beam of magnetic helium. atoms. And I know people who do that for a living, so it's kind of cool. So, but I've never done it. Okay, so yeah.
Professor? So
yeah.
the energy for a given N1 and N2, the energy of the para and orthostates, is that the same?
No. Well, actually, that's a good question. I mean, I would write it like this: if no interactions, and when I say interactions, I mean no Coulomb interactions between the particles. If no interactions, then the energy is the same as you just said. But if I have interactions, then we use that Hund's rule business. And which one is lower in energy?
The one that has the the further apart spatial component.
Which is which? Which is which one?
The orthostate.
Exactly. E ortho is less than E para.
I see. So this is because of the exchange force, as we call it?
Yeah.
Okay.
Although maybe, yeah, that's right. You can call it whatever you want. You could call it exchange force, but it's, it's basically that they're further apart or closer, one is closer, one is further. And so, one will have a higher, it's the Coulomb interaction, it's the Coulomb interaction. But yeah, you could call it the exchange force.
I see. And one other question for a given, I guess, orthostate, could you provide some reasoning or intuition for why we could use any of the triplet states and the physics would be the same? It seems to me that it wouldn't.
The reason is because a triplet state is a spin 1, and so if I have S total is 1, then M total is 1, 0, or -1. But what does that mean? You have these 3 states, M total equals 1, 0, -1. But what that means, it's just this, like this is M total equals 1, 0, -1. So this is M total equals 1, 0, -1. And so these 3 different states are really, it's like a magnet that has spin 1, but the magnet can be pointing up or sideways or down. But the physics of the magnet is the same, whether it's up, sideways, or down. There's no difference in the physics of a magnet. Do you see what I'm saying? That's why we say it's the same, if that makes any sense.
That makes sense. So we don't really care about orientation?
It depends, like if I have a Stern-Gerlach device and I shoot it and I prepare it in one particular magnetic orientation, then when it goes through the Stern-Gerlach device, it will be deflected in different directions. So in that case, we care, but it just depends on the details.
Okay.
Okay. All right.
Thank you.
Professor?
Yeah.
But I had a question. If you do have interactions between the electrons, then all the different L states will not really be degenerate, right? In the spatial wave function.
All the different L states will not be degenerate. No, I think that's when we talk about the L states, those are the eigenstates of the single particle Hamiltonian. So when we talk about the eigenstates of the single particle Hamiltonian, we do not care about the interactions between the particles. That's something that plays a role after. Does that make sense?
Yeah, but I remember that I'm from chemistry. When we add electrons to a nucleus, the L number also plays a role. So, and the lower the L is,
Wait. The L is playing a role here. Wait. I'm sorry. The L is already playing a role. Look, it's 2LM. There's L's there. I'm saying the L is already playing a role.
But are all the L's of the same energy?
There's a rule. It's the rules of atomic physics. I mean, I have psi n L m, and the rule is that if I have n equals 1, then I have L equals 0, and there's only 1. But if I have n equals 2, then I can have L equals 1. But if I have n equals 3, then I can have L equals 2, and I can have L equals 1. If I have n equals 4, then I can have L equals 3, 2, and 1. And so all of these states are degenerate. All right, so it's the rules of atomic physics. And those are the rules that I need you guys to go back and review and memorize for this course, because we're going to be using them like crazy. Okay, but now let's start a new topic. And the new topic is perturbation theory. So we're going to talk about time-independent perturbation theory. All right, so that's the new topic. And so this is a really big topic. So this is like a really big moment in this class, because this is like really the biggest topic of this course, I would say, is perturbation theory in general. So this is a really important topic, hugely important. And the idea of perturbation theory is that it's really, the idea is that it's really hard to solve quantum mechanics problems. And so the only problem that we can solve in quantum mechanics, there's not very many problems that we can really solve. The solvable quantum mechanics problem, it turns out there's really only one problem that we can solve. Does anybody know what it is?
The hydrogen atom?
The hydrogen atom is an example, but what is it more generally?
The particle in a box?
The particle in a box is an example, but what is it more generally?
Single particle problem.
The what?
Single particle problem.
Oh, no, that's a little too general. That's a little too general.
Infinite square well?
The infinite square well is an example of what more general problem. But single particle problem is like a little too general. Come on, there's only one left that you haven't mentioned.
Harmonic
Spherical?
oscillator.
Say it again, what?
Spherical potential?
Well, it depends what spherical potential you're talking about, you know. But okay, but you're right. It could be a spherical potential. But here, okay, maybe it's a trick question. Simple harmonic oscillator. See that, and I guess that's a trick question because I have not been talking about the simple harmonic oscillator. But you guys all know last semester you did particle in a box, you did simple harmonic oscillator, and you did Coulomb potential, right? Those are basically the only three problems that you solved last semester. Oh, and then you did free particle. All right, so you did four. You did particle in a box, Coulomb, simple harmonic oscillator, and free particle. So there's 4 problems that you solved last semester. And you probably thought that was only the first 4 of many, many problems you'd be able to solve. But there's a trick we played on you, which is that those are the only 4 problems that anyone knows how to solve. And it turns out that all 4 of those problems are really only one problem. They are all examples of the simple harmonic oscillator. So it turns out that really the simple harmonic oscillator is really the only problem that we can solve in quantum mechanics. And I'm not going to like show you why. You know, like the atomic, the Coulomb problem really is a example of the simple harmonic oscillator if you do a really fancy exchange of variables. You can actually show it, but it's hard. You know, it's like a really hard graduate level homework problem. And I remember because I had to do it in graduate school, so I'll never forget. It was quite tedious. Okay, so the bottom line is that there's not that many problems in quantum mechanics that we can solve. They're basically just the simple harmonic oscillator. But in nature, many things are not a simple harmonic oscillator in nature. Everything is not. All things are not simple harmonic oscillators. There are many things that are not simple harmonic oscillators in nature. An example, some examples are, for example, anharmonic oscillators. And what is an anharmonic oscillator? Well, an anharmonic oscillator is just one that, well, let's take an example. I mean, if I have a potential energy of a particle, and if the particle has a potential energy 1/2 kx squared, where k is a constant, what do I call that particle? Someone tell me. I'm asking you a question. If my potential looks like this, I just underlined it, then what do I call that particle? It is a what?
A scattering particle.
Well, no, scattering is sort of like when your energy is above the vacuum level and stuff. No, that I'm asking, you could scatter from this potential, but I'm asking a different question. What do I call this particle?
Harmonic oscillator.
Spin?
Exactly. It's a simple harmonic oscillator. That is the definition of a simple harmonic oscillator. Okay, so again, another trick question. I like to ask you trick questions. So, but now if I add this term to it, now is it still a simple harmonic oscillator? Yes or no?
No.
That's right. So as soon as I add this, it's no longer a simple harmonic oscillator. So this I'll call the anharmonic term. And in nature, anharmonic terms are very common. I mean, an example, and I won't derive it for you, but for example, you guys have all heard of a thermal expansion, right? I take a crystal, I take any material, I heat it up, it expands. I take a crystal, I cool it down, and it shrinks. Yeah, you guys all know that, right? You've all experienced it. That occurs because of the anharmonic terms in the interatomic potentials. There's anharmonic terms. Without anharmonicity, you would not have thermal expansion. So just, so every time, you warm something up and it expands, you should think to yourself, oh, anharmonic oscillators are in there. So there's many examples. And there's other things, for example, like you can have, electric and magnetic fields that are strangely configured that are not harmonic oscillators. You could have weird spikes. You could have spiky potentials. Spiky potential? Like an example of a spiky potential would be, for example, suppose I have a particle in a box and I put a delta function in it. A delta function, V of x is equal to delta of x. All right, that's like a spiky potential. That's not a harmonic. That's not a harmonic potential. And suppose I had free particles. Suppose I have multiple particles with Coulomb interactions. Then from multiple particles, then it becomes a big mess, and it's not just a simple harmonic oscillator where if I have the Coulomb potentials between them all. So there's many examples that you cannot fit into just a simple harmonic oscillator picture. And so these are very common in nature. And so the point is, how do we solve? And the answer is we use perturbation theory, because you cannot solve these problems. Many of these problems you cannot solve just using the simple things you learned last semester. And I could say to you, so it's easy for me to give you some new Hamiltonian, and I just ask you, what are the eigenstates of this new Hamiltonian, where this is not a simple harmonic oscillator? And then I could say, solve this. And then you would say, I don't know how. Okay. So that's the crux of the matter. We are often confronted with this situation where we want to solve this, but we can't, because it's not a simple harmonic oscillator. And so then what do we do? What do we do? So the answer, of course, is we use perturbation theory. And so the question then becomes, what is perturbation theory? And so it turns out that perturbation theory is a trick. It's a math trick. But it's actually more than just a math trick. But at heart, it is a math trick. It's a math trick, and it's useful. It's a useful trick when I can do something. It's useful when I can write the Hamiltonian that I want to solve is equal to a known Hamiltonian plus some perturbation, I'll call it H prime, where H prime is small. And small means it's a lot smaller than H naught. So when I can write the unknown, so H is unknown, the unknown Hamiltonian, if I can write the unknown Hamiltonian as a sum of a known Hamiltonian plus what I will call the perturbation. When I can do this, then perturbation theory works, or usually works. Okay. So that's the starting point of perturbation theory, is I want to be able to write my unknown Hamiltonian as a known Hamiltonian plus a perturbation. And what does it mean to be a known Hamiltonian? A known Hamiltonian has the following property. If I hit that known Hamiltonian up against its eigenstates, then I know the eigenstates. And so I'll call them 0, 0, 0 to say that these are the unperturbed eigenstates. So that means I know, so for Hamiltonian to be known, it means that I know the eigenstates and I know the eigenenergies, okay? I know these things, okay? So these are all known. That's what it means to be known. It means that you've solved that problem. And basically it means that it's either a free particle, or it's a simple harmonic oscillator, or it's a particle in a box, or it's an atomic state. Because these are the known ones. These four, it's one of these four. So, okay, so that's a known Hamiltonian. Okay, so how do we, okay, so let's talk about it some more, because so if I can write my unknown Hamiltonian, so as this, as a known Hamiltonian plus an unknown perturbation, when I say an unknown, so H prime is equal to an unknown perturbation. What I mean when I say unknown, I just mean it's not, I don't know, it just means that I don't know the eigenstates. I don't know the eigenstates. If I can write my Hamiltonian like that, and if I know that H prime is small, then something useful happens, because what I can do is I can do this. I can, in my mind, I can think of this. I can think of, we can consider the following picture. The following picture is true. The following picture is usually true. Following picture is usually true. And the picture is this. This is the picture that I want you to have in your head. The picture is that I can think of the Hamiltonian is H naught plus lambda H prime. Let's consider, and let's just consider lambda is, we'll just call it we'll just call it a variational parameter, which varies from 0 to 1. So if lambda equals 0, then my Hamiltonian is the known Hamiltonian. And if lambda equals 1, then my Hamiltonian is the Hamiltonian that I care about. This is the one we want to solve. Now, for us to solve a Hamiltonian, it means that this is what we want. We want to know if I have H acting on some states, psi n, then those states are equal to some energy times psi n. This is what we want. Okay, this is what it means to solve a Hamiltonian. We want the eigenstates. We want the eigenstates. That's always the most important thing in quantum mechanics. We want the eigenstates. And so if I can write it like this, like this, then the important approximation is that I can say that psi n, I can write it as it's basically a function of lambda, and En is also a function of lambda. And that's it. That's all. It's actually kind of simple. And that's sort of is kind of trivial, but let me show you what that means. It means this. It means that I can take my unperturbed Hamiltonian, and remember, I'm going to have all my states. I'm going to have psi 1 naught, and it has energy E1 naught, and I'm going to have my eigenstate psi. I have my eigenstate psi 2 naught with energy E2 naught, and my eigenstate psi 3 naught with energy E3 naught, etc. Those are all my known eigenstates. And now I have my unknown eigenstates here, and I have the first one, and it has the unknown and eigenenergy. I have the second one, it has the unknown eigenenergy. I have the third one, it has the unknown eigenenergy, etc. So these are the unknown ones, and if this is true, if I defined my Hamiltonian as equal to h naught plus lambda h prime, and if my eigenstates and eigenenergies are functions of lambda, then that means that as I vary from, this is lambda equals 0 on the left, and this is lambda equals what on the right? Lambda equals what?
1.
Yes. Then the idea is that each of these states is connected. I can transform continuously. This is kind of an abstract mathematical way of thinking about it, but this is the foundation that underlies perturbation theories, this physical picture. And it's actually really important to kind of think about it a little bit. So the idea is that I can smoothly transform from one state to the other, smoothly transform and the idea is that I can that each state smoothly transforms to the other. And it must be true, because if this is true, then this is true, because that's what it means for these states and energies to be functions of this variational parameter lambda. It means I can smoothly transform from the unperturbed state to the perturbed state. And why is this important? The reason it's important because if that is true, I'll write it here again, h equals h naught plus lambda h. If that is true, then that means that I can write this. I can say that psi n is equal to a Taylor expansion, because then I can say psi n, the unperturbed state, the perturbed state, perturb, can be written as a Taylor expansion, lambda to the 0th power of psi n 0 plus lambda times psi n1 plus lambda squared times some psi n2 plus lambda 3 times some psi n3 plus dot, 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 all the way to infinity. And by the same token, the unperturbed eigenenergy will be lambda to the 0 times En0 plus lambda to the 1 power of times En1 plus lambda squared times En2 plus etc. times En3. Okay, and so this should be, so this is a perturbation expansion. This is my perturbation expansion. Perturbation expansion, and my perturbation expansion is just a Taylor expansion. And you guys have all done Taylor expansions.
Professor?
Yeah.
Just a quick question. Why are we claiming that the transition needs to be smooth? I mean, I can't imagine why we can't have lambda be 0 all the while and then discontinuously jump to 1 at the very end or something like that.
No, but the question is, can I define lambda that's very small and have it just go from very small and make it bigger and bigger to 1? Can I do that? And so it's just a mathematical property. So I could pick, if I pick some H prime, then because okay, so here's the thing. It's like, this is the way to think about it. Consider a phase transition. Consider a cup full of water. Mm-hmm. I'm decreasing the temperature. The water is still water. I'm making it colder and colder. I'm continuously transforming it. And so it's just like a simple Taylor expansion. But then I hit this magic temperature, the temperature of freezing the water, and suddenly turns to ice. Now that's discontinuous. So that means that the Taylor expansion doesn't work. That's not a smooth transformation. I can smoothly go from hot water to cold water, and just intuitively, but I cannot smoothly go from hot water to ice. And so that means that what I'm saying is that there can be no quantum phase transition. You cannot, if there's a quantum phase transition, meaning that as I vary a parameter, if my quantum mechanical system suddenly reorganizes dramatically, then perturbation theory fails. And I'll give you a physical example. An actual physical example is superconductivity. So if you take a metal, a chunk of copper, or let's say a chunk of lead, and I cool down the lead, and if I measure the electrical resistance, as the lead gets colder and colder and colder, then the conductivity smoothly goes down. But then as I hit a magic temperature, then the electrical conductivity of the lead goes to 0. It becomes a superconductor. And that is a transition. That is a quantum mechanical phase transition. And so in order to figure out why the resistance of lead goes to 0, it took, and I think I've mentioned this in class already, it took people 50 years to do that. 50 years, 50 years. People were thinking hard, and the smartest people in the world were thinking about it. Einstein was thinking about it, Richard Feynman was thinking about it, and they failed. They could not solve it. It was too hard for them. It was too hard for Einstein. It was too hard for Richard Feynman. The reason it was so hard is because they could not apply perturbation theory to it. They tried to solve it using perturbation theory, because perturbation theory is how everybody approaches every problem. It would not work because there was a quantum phase transition. And so somebody else, Bardeen, Cooper, and Schrieffer, in the 1950s, they threw away perturbation theory and they said, well, let's not do perturbation theory. Let's try to solve it in a different way. And they solved it and got a Nobel Prize. So, if sometimes perturbation theory doesn't work, and if you can solve one of those problems, you get a Nobel Prize. Okay, so for most situations, the perturbation theory works really well, surprisingly well. but there are situations where it does not work. But the point, okay, so the point is that the idea, really the most important thing is not all this fancy math. The picture that you really need in your mind is this connection right here. This picture that I've drawn right here is really the most important thing. For perturbation theory to work, I can attach every unperturbed state smoothly turns into a perturbed state. And by the same token, every unperturbed eigenenergy smoothly turns into a perturbed eigenenergy. That's the intuitive picture that I want you to remember. Now, this Taylor expansion business, all this mathematics, that's the underlying mathematics of this intuitive statement. So because you're students in an undergraduate class, you're going to have to work through the underlying math. But I'll just tell you, a year from now, you're going to forget all of the underlying math. But what I want you to remember is the intuitive picture. But you cannot remember the intuitive picture until you go through the math. I mean, that's the way human brains work, right? You got to go through the math, and then you feel very happy. It's like, oh, I went through the math. Now I feel very comfortable. And so now I can remember it. At least that's how I am. I think that's how most people are. As an undergraduate, you go through the math, and then you forget the math, but you remember the simple result. And that's what we're about to do. Although we got to end. But we're going to end now. But what we're going to do in the next class is we're going to basically take this perturbation expansion and we're going to solve this problem. H psi is equal to E psi, okay? That's the whole name of the game, is to solve that problem. And we're going to solve that problem using perturbation theory. And that's what we're going to do next in the next class. Okay. Bye.
Professor, right, one quick question
Yeah,
about what you've written here. Does this only work because we're like in a time independent case? I guess I'm trying to understand what lambda represents. Because it seems to me, because H and H prime are energies, and so is H naught, right? The Hamiltonians indicate energy. So I guess what I'm asking is does this only really work with this lambda that we've created because we're in a time independent case?
Okay, well, let me answer that question. I mean, do you have a moment? I mean, I would like to spend like 3 or 4 minutes answering that question. Because the easiest way is just to write something down. I mean, there's a really simple answer to your question, but okay. Can you wait for the office hour? Is that okay?
Yeah, I have class in 7 minutes, but if office hours will start before that, then yes.
Okay, well, actually, let's see. I can just do it like this. I mean, look, here's the example. Okay, suppose I said, I have a potential that looks like this. V of x is equal to 1/2 kx squared plus 1/100th kx cubed, where it's the same k, okay? And now I say to you, I want you to tell me what are the eigenstates and what are the eigenenergies of this potential, okay? And so what you would say, or what you should say is, I have no clue. I cannot do this because I know this one, that's a simple harmonic oscillator, but now that you put an x cubed there, it's no longer a simple harmonic oscillator. So the bottom line is you cannot solve this. This is too hard for you to solve, all right? Because it's not one of the 4 problems that you did last semester. But then you might say, I think I can solve this using perturbation theory. And to solve this using perturbation theory, basically what I'm saying is my Hamiltonian is p squared over 2m plus 1/2 kx squared plus 1/100th kx cubed. That's my Hamiltonian, right? And I'm asking you to solve it. And so what you would do is you say, okay, this one I know. That's H naught. I know that. That's just a simple harmonic oscillator. That's a known one. And this one is, I'll call H prime. And the first thing you'll notice is that does it satisfy H prime is way less than H naught? And the answer is yes. And so that's good. So that means it should solve, that means that perturbation theory should apply. But for perturbation theory to apply, what that means is that if I take the Hamiltonian of my known Hamiltonian, the simple harmonic oscillator states, psi 1 naught, psi 2 naught, you know, etc., then that means that I should be able to link them to some new eigenstate, psi 1, psi 2, etc. And I should be able to link them as I vary lambda from lambda equals 0 to lambda equals 1. So in your own mind, you could just say, well, what does that even mean? Well, that means that here, let's call this factor right here. I can call that, I don't know, I'll call that C times, like this is like my lambda. So I could say, suppose I had H prime is equal to, H prime is equal to 1/1,000,000th of kx cubed. What's the solution? Solve it. Suppose I had H prime is equal to 1/100,000th of kx cubed. Suppose I had H prime is equal to 1/10,000th of kx cubed. What I'm saying is solve all of these problems and they should smoothly transform as I smoothly increase that perturbation. Then if I take it all the way to 1/100th kx cubed, then what I'm saying is there should be a smooth transition. Do you see? And so it's like a mathematical statement. I'm saying if I find the eigenstates for H prime equals 0, and I find the eigenstates, and then I find the eigenstates for H prime equals 1/1,000,000th, and then H prime equals 1/100,000th, 1/10,000th, 1/100th. What I'm saying is that the eigenstate there should be like a smooth variation from one to the other. There should be some variable lambda that if I was to like solve it for the arbitrary lambda, I should be able to smoothly vary. So I guess what I'm basically trying to say is, if I solved instead for this, p squared over 2m plus 1/2 kx squared plus lambda kx cubed, then I should be able to smoothly vary lambda from 1/1,000,000th to 1/100th. Do you see what I'm saying? And the state should just smoothly vary, and the energy should smoothly vary. That is sort of the underlying mathematical foundation of perturbation theory. And it is usually true. It usually works, but it does not always work. Does that answer your question?
That does. Thank you so much. I'm sorry for extending the recording. Thank you very much.
That's okay. No problem. Okay. Bye-bye.
Thank you, Professor.
Bye-bye.